now the recording is started, and it is our basic chemistry concept. So for the basic chemistry concept, we will be using the same or the content we have used so far in the lecture slide. So all the equations and the informations will be needed here as well to solve the problems here. And these problems you will find mostly it is very simple, that mostly probably you have done it your high school or pre-uni. The reason to put it here is to make it uniform, so that from when we start from here, because you will not see me talking more or detail about the molarity, that concentration, how to make the solution. I would not have that much time to go again and again and again to the come back and go. I mean back and forth. I will not have that much time because we have quite many things to discuss. So those who are not familiar with, please let me know so I can make a special arrangement for you guys only. That is, and another thing is just a suggestion. This is not part of the teaching here or content, our learning things, but just for general thing all over. Some students are very shy. They don't want to come forward and say, okay, I don't know that. There is no problem. There is no shyness to tell that you do not know. If any student says that he knows or she knows everything, then be sure that he or she has problem. If somebody said that I do not know, that means he is or she is a normal person. All right. And you sometimes many students say that I'm scared, I'm shy, that what other student maybe. Believe me, others also do not know. They just pretend that they know. Okay, so be the first one to come forward and say that I do not know, I don't understand this one. Can you please explain more? There is no shyness in that. There is no problem in that. And another thing is, you do not expect or do not think that you are the headline. So everybody is saying that, oh, you know that he does not or she does not know. Nobody is going to say that. All right. So only you will correct yourself, nobody else. Or in this case, your teacher in Swinburne, your teacher will correct you, none else. If you go and talk to somebody in the public, you make mistake, they will laugh, they will never tell you that you are wrong. They will only make fun of you. That's the thing. Here, we will never make fun of you. We will just correct you. We will say that this is not in this case. It will be like that way. So trust us, okay? And don't be shy. Don't be scared. Nothing. We are here to help you. We are here so that you can learn more. All right. So this is what I am to say. Now, the thing is the molarity, concentration, number of particles, Avogadro's number. These things are well taught. I think it has been discussed in the high school. So I assume that many of you know. If you do not know, if you need some rehearsal on it or you want to refurbish your knowledge, we are here to discuss. I'm more than happy to discuss actually. If somebody said that, can you please discuss or tell something more, I will be more than happy. Okay, so this tutorial thing is already published on Canvas. So I'm hoping that everybody has a copy of this. I cannot see your face, so I do not know how is your reaction now. So I hope that you have taken it positively and you have the copy of it. So these are the formulas. Let me take the pencil from here. All right. So these are the formulas that we will be using, and I'm sure that you are very well versed with these formulas as well. How to find the number of moles? All right. From the particle number or from the mass, from if it is a gaseous, for gas in gaseous phase, we can also find the number of moles. And this is one way, right? This is another way. if we know it is an STP or SLR. These two terms you should be comfortable with, because sometimes in the exam, in the test, we will just tell STP or SLR. STP means standard temperature and pressure, which is 0 degrees centigrade and 101 kilopascal. SLR is standard lab condition. It's 25 degrees and 101 kilopascal. The thing is, how to remember this thing? STP is standard temperature and pressure. Standard temperature is standard at 0 degree everywhere, everywhere in the world 0 degree. But lab condition, we cannot have the lab condition 0 degree at every place, right? Malaysia is a tropical country, so we don't have that cold temperature. However, in Nordic countries, they have cold temperature, so they can use the standard temperature pressure. But mostly in the lab, if it is 0 degree, probably nobody will stay there. But SLR means standard lab condition. All right. So the lab condition means at 25 degrees, which is very convenient for us to do our work, 25 degrees, right? So, but temperature, pressure for both cases are same, 101. Only the two different things that you should be very careful in taking note that here at STP is 22.4 liter per mole. At 1 mole, we'll have the molar volume, that Vm is molar volume. One molar volume is 1 mole, volume of 1 mole gas. So 1 mole volume of the gas will have 22.4 liter. Whereas at 25 degrees centigrade, it is higher because the temperature is high. So at high temperature, it expands, right? Everything becomes expanded at high temperature. So Vm becomes 24.5 liter. So it is a little bit higher, but higher nonetheless. So these two things you should be comfortable with. Is there any question anybody has as of now? I cannot see your chat box, so you need to talk.
Sir, can you explain on question 4 of objective question letter?
I'll go there. And thank you. I don't know who is there, but thank you very much. I appreciate that you unmute yourself and talk. So probably some students does not want to talk. So I'll start from very beginning, from number 1, and then I'll go all the way to question 15 and some of the questions from the previous year. All right. So let's start from the self-testing question number 1. The atoms, carbon 12 and carbon 14. All right. Do you know, have you heard about carbon 13? Anybody? Just as I'm here, I cannot, I think I can talk about it. Carbon 13, have you heard about it? Carbon 13.
No.
No. Do you know that the prehistoric or ancient things like the artifacts that we can dig out from the past civilization, we do the carbon 13 dating. Have you heard about it? Carbon 13 dating. That means in the lab, it is analyzed that how many % of carbon 13 is there, and then have reached the half-life of that carbon 13. And based on that, the age of that artifact is actually determined. Like this is 2,000 years old, or 5,000 years old, or 10,000 years old. So carbon 13 is very useful tool for carbon dating, to know how old exactly is the artifact. Anyway, for this case, carbon 12 is the most prominent, that all the carbon is C. right, is the carbon-12. Mostly are carbon-12, very small percentage carbon-13 and carbon-14. So carbon-12 and carbon-14 are regarded as isotope of the same element because their atomic number different. What is an atomic number? Atomic number is the proton number, right? If the proton number changes, that means that is not the same element anymore. Proton number changed by just one indicates that it is these two are the not same number. All right. So A is not the answer. B, atoms have the same mass number. Since they have 12 and 14, that means they are, although the proton number is same, but their total mass number is different. So of course their mass number is different. It is not the answer. C, atoms have similar physical properties. In that case, probably there is a similar properties, but we do not for sure know that how similar the properties are for them, right? And most of the time, when they are different isotopes, they do not have the exact same property. They have some different properties. Atoms have different neutron number of neutrons. Yes, because their proton number is same and neutron number is different. That's why they have different number of mass. So D is the correct answer. If you have anyone has any question, stop me right away and then ask the question, just like someone asked me. Question number 2 says that X is an atom, ion, with 40 protons, 41 neutrons, 43 electrons. Right? So most likely has the following nuclear symbol. 40 protons. Where is the proton number? It should be. It is actually, did I tell yesterday that on the basic left side base is the number of proton. Okay. And this is a mass number here. Whatever will be here is the mass number on top left corner. On right side is the charge. If it is a negative charge or positive charge. So 40 protons, that means A, B, C, D all are having 40 on the left hand corner, bottom corner, left side, bottom corner. So all are, this is correct, that 40 protons are 41 neutrons. So it should be the mass number. And this mass number here is 40 plus 41, right? 40 plus 41, total is the mass number. And that makes for 81. So this is 81. This is 81. This is 83, 81, 41. So these two probably either either of them is correct. Both cannot be correct because it is 0 here, no charge. Here it is carrying 3 charge. Now we have found out 2 criteria that is supposed to find out. From these 2 clues. And then another thing is says that 43 electrons. 43 electrons. So 43 electrons means it has 40 proton. Each proton is carrying 1 positive charge. Right? Each proton is carrying 1 positive charge. 43 electrons, each electron is carrying 1 negative charge. So which one is more? Electron is more, so that negative charge should be more. So 3 negative charge should be excess. So that this is the correct answer. Because here it is 0. Here it is 0, it shows. So it cannot be the correct answer. Oh. And then here it is 3. So it is the correct answer for this case. Right? I hope it's clear. Question number 3 says that assume the lead consists of 3 isotopes having the abundance of masses given below. according to this data, calculate average atomic mass of lead. Now we have seen the relative atomic mass from the equation that AR, usually AR is difficult to write because AR sometimes say argon, but we are not talking about argon. So AR should be the sum of the percentage times the abundance. Abundance percentage times the relative atomic isotopic mass. So we will sum these two, 203.917, 203.97. You understand this is 0.97. All right, times 1.48. 1.48, and then 0.48, and then plus it will go on like this, 205.97 times 23.6 here, and then plus 206.98 times 22.6. So in this way, and then at the bottom, or it will be divided by the sum of the abundance all. 1.48 plus 23.6 plus 22.6 plus 52.3. So in this way, we will find that the mass or average atomic mass for that element is 207.18 in that way. All right. Let me finish my food first. It's getting cold. Question number 4 says that some information about the element rhenium is given in the table below. Given that the relative atomic mass of rhenium is 186.2, relative atomic mass, that means it has considered the isotopic mass plus the fraction of abundance, right? The if it is 186.2, the percentage abundance of 187 rhenium is closest to, so what is the abundance percentage? It only says that the atomic mass, relative atomic mass is this, but percentage abundance, what is the percentage abundance will be there? So here, I mean, if we follow this thing, right? So it is, AR is actually, for this case, is 207, right? AR is 207 here. 207.18. This is the rhenium. Oh, not the rhenium. So for this case, it says that we did not know for this case the average mass, but for this case, we know the average mass, atomic mass. So 186.2, all right, is equal to what? Is equal to the percentage of abundance times the isotopic mass. But if we convert the percentage of abundance into fraction, right? For this case, we just considered 1.8448%, 23%, 22.6%, 52.3%. We could also like this. What is that? Here, if you have seen it, let me find it for you. What is that? I just saw it here. Oh, here. So here you see that 8% and 92% considered as it is, right? 8% and 92% considered as it is, right? But we can also consider the fraction of it. 8% means how many? I mean, fraction of is 8 over 100, right? 8 over 100 is 8%. 8 over 100 is 8%, which is actually 0.008, 0.08, not 008, 0.08. Same goes for 92%, 92 over 100.92. So if we just multiply with the fraction, with the relative atomic mass, we also can find the relative atomic mass, average atomic mass, sorry. So in the same way, if we do not want to divide it by 100%, we can just consider the fraction of it. Okay, we can just consider the fraction of it, and then this fraction will be 185, which is relative atomic mass. Okay, it says that 187. We want to know 187, right? 187. So 185. Let's consider that this fraction of percentage is X for it, right? Then the other must be 187. 187 must be the fraction of the rest. Rest means 1 minus X, right? Because whatever altogether it should be 1. Right or not? Is that okay so far?
Yes.
Good. So now if we equate this problem or this equation, all right, if we equate this equation, we will see that it is 0.6 later. I hope that it is big enough for you now. It is 0.6 it is coming out of. Okay, 6, which is 60%. Converted to percentage, from fraction to percentage is 60%. Right. So this is the answer. I hope that is clear now. Question number 5 says the percentage by mass of calcium in the compound of calcium sulfate is approximately what? How do we find it? Mass of calcium by total mass of calcium sulfate times 100%. That will be the percentage. Can anybody tell me what is the mass of calcium sulfate? Can anybody tell me what is the mass of calcium sulfate? Can you try to calculate it? If you do not know, still you try and make mistake, that is, I'm happy to see that one actually, no problem. Can anybody please tell me what is the mass of calcium sulfate? Do you know how to calculate it?
136.15. Hello? 136.15.
Oh, all right. Okay, so Anybody, does anybody agree with him? I do not know who is talking actually, sorry. But your friends know that you are talking and you're contributing actually, that's good. So anybody disagree or agree with him who is talking? How do you find it? Can you please explain? How do you find 136?
I added everything. One calcium, one sulfur, and 4 oxygen.
Exactly, that is good. Thank you very much. That is exactly what I wanted to know, that how do you find it? Of course, it is very easy to find from Google. You just Google it, you will get it. But we need to know how, right? So calcium is 40, right? I'm just rounding off. But in the test or exam, you will be given the periodic table. So be resourceful in that way so that you can be more precise. 40 plus sulfur is 32. Should I be showing you as well? How do we find it from where? You know, from the periodic table we saw last class, right? The periodic table, and in the periodic table it is given the atomic weight. So atomic weight for sulfur is 32. I think, yeah, around should be some fraction, but I do not know exactly. And there are oxygen, 4 oxygen is there. You can see there are 4 oxygen is there. Okay. There are 4 oxygen is here. So 4 times 16. 4 times 16 is what is the total mass of this molecule. You may differ with me that, okay, I'm taking the number of atoms, I mean atomic mass, and then I'm telling is the molecular weight. Yes, because all these 3 atoms in this proportion, they made up this molecule. So altogether, Eric, what is the, you just say 130?
I deleted it. I think it's 136.15.
Okay. 136.15. Thank you so much.
Yeah, added with the decimals.
Okay, I think I did not take the fraction. So if we take the fraction, 136.15 it will be. Now this is the mass of calcium sulfate. And what is the percentage of calcium in calcium sulfate? So what we'll do is 40 over 136.015 by this way and times 100%. So in this way, it will give you 29% of calcium sulfate is there. Calcium in calcium sulfate is there. In this way, we can also ask you that how many percentage of sulfur is there? So you know that you have to divide 32 over this 136 that way. Now, can anybody tell me, actually the answer are given already, but is there anybody want to show or explain how do we find for this question 6?
Calculate them one by one.
Okay, yes, that is the only way. Otherwise, we are not a fortune teller that we can tell, look at it and say, right? So you are scientist, you're going to be engineer. So you have to show it proof with calculation. And then if we do the calculation, I cannot touch the mouse right now. My hands are messy. So ammonium nitrate. What is the total mass of ammonium nitrate? Can anybody tell me? Can anybody tell me with calculation? I have a very bad habit, you know, to name calling and ask question. It's not to shame you, but just to make the class more engaging and interactive. So if I usually do not, I try not to do it, but if I call the name and ask, then only student talks. So that is also rewarding for me. So anybody who wants to say how much is the molecular weight of calcium, ammonium nitrate?
The mass is 35.02.
Ammonium nitrate 35.02.
Yes.
Can you check once again? Like there are nitrogen 1, right? 2 nitrogen. How many hydrogens are there? There are 4 hydrogen. And then there are 3 oxygen atoms are there, right? So in this way, nitrogen is 14 each. The molecular atomic weight, nitrogen is 14 each. Hydrogen, so 2 nitrogen 14 times 2 is 28. And then hydrogen is 4, so just round off to 4, 1. So 4 hydrogen each one, so it's 4. So 28 plus 4 is 32. Plus there are 3 oxygen, that means each is 16. 48 should be added there. So how much altogether?
35.91.
Yeah. Hey, have you ever taken this Laksa delivery? On delivery, anybody has an experience of that? It is not good when it's cold, right?
Yep.
Yeah. And that's why I'm saying that whoever have not tried Laksa must try once. And then you will try yourself. Nobody need to tell you. But only problem is it's quite rich actually because of the coconut milk. Please allow me a few minutes. I just clean my hand first so that I can start better. Okay, just 2 minutes. I'm done. Now can start. And by the way, I forgot. I hope that I hope that you have your lunch, and I did not make you hungry. Feel hungry, but if I did, that is good. You should eat more and also study more. Okay, so now, what is that? Okay, So ammonium nitrate altogether is what? How much you say? Somebody says, I think. No. Monab says that sorry, it doesn't matter. Yeah, it's okay that you join. Okay, so ammonium nitrate. Can anybody say how much did you say? So 14 times 2. Then plus 4 for hydrogen, and then plus 48. Altogether is how much? I don't have the calculator with me. $80.
80.
Yep, 80. So ammonium nitrate is 80, and how much of the nitrogen is there? So nitrogen is 28. 28 gram of nitrogen in 80 gram of ammonium nitrate. So this is the percentage. So in this way, we have to find the percentage and times 100%. How much is the percentage? So we can find the percentage here. How about urea? Here there is 1 carbon, 1 oxygen. There are 2 nitrogen and 4 hydrogen, because this 2 is upon all these 2, right? Nitrogen and hydrogen. Upon nitrogen and hydrogen both. This 2 is covering nitrogen and both. So in this way, we will be finding the nitrogen, the total mass of this. So it will be 14 times 2 plus 12 plus 4, because 4 hydrogen are there, plus 16. 1 oxygen is there. Altogether, in this way, we have to find the total mass of urea, and then the nitrogen is 1 nitrogen is there, right? So if we find, and then the least thing, I think, the least thing student or anybody will consider ammonia. It looks so simple, only nitrogen and hydrogen, but interestingly, it has the most percentage of nitrogen here. Most percentage of nitrogen in ammonia. Does anybody know what is ammonia used for? Do you know what is ammonia used for?
Fertilizer?
Yeah, fertilizer. That's good, thank you. So actually urea is a very good fertilizer. Ammonium sulfate is a good fertilizer. Ammonia is used to produce not only fertilizer, there are many other uses, but fertilizer is the most. Maximum uses of fertilizer is ammonia. But this is also very dangerous, because all of these A, B, C, D, these all are used to produce some kind of explosive particle material. So this is also dangerous in that sense. Okay, so question number 7, an organic compound is known to contain only carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen. The compound contains by mass 39.1% of carbon and 8.7% of hydrogen. What about the oxygen? It doesn't say anything about oxygen. The number of carbon atoms in the empirical formula is the empirical formula. It does not ask you for the molecular formula, only the empirical formula. So how do we find the empirical formula? What do we have to find out first? Can anybody tell me? What is the first thing that you will be looking for when you are calculating the empirical formula?
The mass.
Yeah, mass. And then the next step is?
Number of
Number of
moles.
moles.
Sorry?
Number of moles.
Number of moles. That's great, Vanessa. Yes, if we do not know the mass, we will never be able to know the number of moles. So both of you, thank you. So what we will do is the simple way we will try to, simple but steady and foolproof way we will try that we write carbon here. It is hydrogen here. Excuse my handwriting, but you understand what is meant, right? And then oxygen is here. So let's say it's carbon, it's hydrogen and oxygen. So mass or weight, M. What is the mass of carbon here?
39.1.
That is the percentage. Can we use for as a mass as well? Yes, we can. Because it says that percentage means out of 100, right? And when it says that by mass, the percentage is this, that means out of 100 mass is gram, out of 100 mass gram, there are 39.1 gram of carbon is there. So we can comfortably just use as it is. So 39.1. So is that clear, everybody, that why we are using percentage to mass? Once again, this 8.7% it says, right? But it says that by mass. It doesn't say by volume. If it is by volume, then there will be a different case. I think we'll deal with it later. But by mass means the mass. Out of 100 gram, there are 8.7 gram of hydrogen. Out of 100 gram, there are 39.1 gram of carbon. That's why we are calling it percentage. So we are considering there is no other information given how much is the total mass of the compound. So we comfortably say that, okay, let's say that there is 100 gram of compound. Since it is mass, a percentage, we consider 100% and we just say 39.1 gram of carbon. And the same way, 8.7 gram of hydrogen. What is the rest? How much of the oxygen will be there? How do you find the oxygen? Is 100 minus 39.1 minus 8.7. What does it make? I don't have a calculator with me, but I can use my phone.
52.2, sir.
Thank you so much. You saved my time. So 52.2 gram of oxygen is there. Now we have to find out the number of moles. And as we have seen from the equation, number of moles is mass over molar mass, right? So we divide by, this is gram, and molar mass of carbon is 12.01 gram per mole. Gram per mole. Right, gram per mole. So this gram and gram will cancel out, only mole remains, and then mole from denominator it goes to the numerator. So that mole is the unit, it becomes the unit. So that is satisfying our need. So if we divide 38.1 over 12, and this is how we will find the number of moles. How much will be the, yeah, it will be 3.25 moles. It will be 3.25. We don't have enough space here, but I hope that you can do it yourself. 3.25 moles. Same goes for hydrogen. Hydrogen is 1.008 to be very precise. I don't remember the decimal places for many cases, but the common elements I do, like carbon, hydrogen, nitrogen, oxygen, all those things. For oxygen is 15.99, right? 15.99. Usually, most of the time we will just round up to 16. So this way we will find the number of moles of carbon, hydrogen, oxygen. And then the next step is to find the simplest ratio. How do we find the simplest ratio? We will divide the number of moles by the smallest number of moles among these three. If we had 4 different elements, among these 4, we have to find out the smallest number of moles. And in this case, the smallest number of moles will be the carbon 3.25. All right, because oxygen in this case will be 3.26. It will be 3.26. And hydrogen, you understand, it will be around 8 point something. 8 point, let's say 6. So it is not the smallest, of course. It is 26. So 25 is the smallest one. So we will divide every the number of moles by 3.25. And then therefore carbon will be 1, the smallest number. And hydrogen, if we divide 8.6 by 3.25, so that it will become, what will be the figure? It will become 2.6. It will become 2.6. Let me see here. So if we divide the hydrogen one, carbon one becoming 1, right? Carbon is becoming 1. Hydrogen, if we divide this 8.6 over 3.25, then it becomes 2.6. I think, let me check. 2.65. 2.65. And then if we divide this oxygen with 3.26 by 3.25, it is very, I mean, 1.00000 something. So we can comfortably say it is 1 as well. 1. Now the scenario comes that if we write down the compound, it will be C1, hydrogen 2.65, and then oxygen is 1 as well. But it cannot be this case, right? It means that there is 1 carbon in this compound. There are, 1 carbon atom in this compound. Hydrogen is there are 2.86 atoms of hydrogen there, and oxygen is 1 atom of oxygen. We understand that 1 atom of carbon is there, but how come the atom you can divide into a fraction? You cannot divide the atom into a fraction, right? Although atom can be divided, now we know, but in the molecule, they do not stay in a fraction mode. They must be in a whole number. To get to the whole number, what do? We must continue to multiply it, all of this carbon, hydrogen, oxygen, to some whole number so that we get the whole number. All right. For this case, if we multiply by 2, then carbon will be 2. It does not become 5. It becomes 5.12 or 13. 5.13 it becomes hydrogen. Still the fraction. So if we multiply by 3, then carbon will be 3 and hydrogen will be very near about 8. That means it is 7.999 something. We can comfortably say 8. And then oxygen will be 3 as well. So carbon will be 3 in this way. Hydrogen will be 8. And oxygen will be 3 in that case. All right, after multiplying by 3. Multiplying by 3, the fraction of mole ratios. So in this will be the formula of this. So the question is asking the number of carbon atoms. So the carbon atoms should be 3 in the molecule. All right, is this clear? Anybody has question with this?
Sir, I think they are asking for empirical formula, right?
Yeah,
so supposed to be 1, right?
1. I mean, the question number is 1. I mean, answer is 1, you say?
Yeah.
No, it is saying that the number. Oh, I need to wait. Let me find the eraser first. It is saying the number of carbon atoms in the empirical formula. Right? Number of carbon atom in the empirical formula. Although at the beginning, at the very first, we found that carbon will be 1, but it is not a formula. It cannot be an empirical formula because hydrogen was having the fraction of atoms in it. So when there is a fraction of atom in a formula, we cannot consider it a formula until and unless we find a whole number. And to get the whole number, we keep multiplying with 1, 2, 3, 4, 5, 6 until we get the whole number for everyone, or very close to a whole number, like 0.99999. So in that case, we can round up to the next level. You understand what I mean?
Yes.
Okay. So yeah, that's why it cannot be 1. We must find a whole number for all the atoms in the molecule, and then only we can consider it is the empirical formula. Of course, after empirical formula, we'll find the molecular formula, but that is the different case, right? It is not here. So everybody okay with this? Anybody has question with this?
So the
Yeah.
answer keys, right? In
Yeah.
page 8, right?
Yeah.
In the answer keys for the question number 7, right? It
Yeah.
puts number A. So it says A,
Oh.
so I think it is wrong, right?
Oh, okay. Let me check. Yeah. Question number. What is the question number that we are saying?
7.
This one, right? No, it is wrong.
Yeah.
Sorry, it is wrong. It should be C. All right, C.
Okay.
Because C is the C. Yeah, C. It should be C. That is 3. So that is wrong. Sorry. Take note, please.
Okay.
Okay. Okay. So this is it. Now I have written quite much. I need to erase it first. Anybody has question, please let me know. I cannot see your face, so I don't understand what you are feeling now. Okay, so question number 8, it says that on analysis, a compound with molar mass 60 gram per mole was found to contain 12 gram carbon, 2 gram of hydrogen, 16 gram of oxygen. What is the molecular formula of the compound? Now we are going to the molecular formula of the compound, right? So the same thing now we'll be doing that. 60 molar mass is 60 and found the 12 gram of carbon. So carbon, hydrogen and oxygen, same way. So carbon, hydrogen, oxygen, same way we find, and then we'll do that. The mole ratio will find 12 over 12.1, right? 12 over 12.1, and then it will give us the mole ratio, which will be 1. Let's say hydrogen is 16 over 1.008, so 16 it is, and oxygen is, oh no, sorry, 12 gram of carbon, 2 gram of hydrogen, sorry, it's 2 gram of hydrogen. 2 gram of hydrogen, so divided by 1, I just round up, so it is 2 as well, and oxygen is 16, and is divided by 16 as well. The molecular weight of oxygen, atomic weight of oxygen is 16, so it is 1 as well. So the empirical formula of that is C1 H2 and O1, and since 1 is no need to write, so I'm not writing it 1 anymore. We understand that if there is nothing written, we know that is 1. So CH2O or COH2 in any way, or H2C, you can write in that way, but the correct formula, carbon should come first. All right, carbon should come first in the formula. Okay, so CH2O. This is the formula for empirical formula. What is the way that we should find the molecular formula from empirical formula? This is, here it is given, I think, the answer that we should divide, where is it? We should divide the molecular mass with the empirical formula mass, and then, is it the one? No, where is it? So molecular mass by the empirical formula mass, and then we see how much is the difference between them, or what is the ratio. Let's go to that, whatever. It is given in the lecture slide. All right, so from here, what is the mass of it? What is the mass of this empirical formula? Carbon is 12, hydrogen is 2, I mean 1 hydrogen 1, so 1 for 1 hydrogen, another for 2 hydrogen 2, and oxygen is 16. So 12 plus 2 is 14 plus 16 is 30, right? 30. It is 30. Now it says that 60 is the molar mass is 60. So 60 over 30. And then we find it is the ratio should be 2. So this ratio is 2. We will multiply this formula with the ratio. So if we multiply with this ratio, then it becomes C2, H4 and O2 as well, which is the correct answer, D. It is very tentative to click or tick here the CH2O, but don't make the mistake. Read the question first. OK, it is not the answer. So D is the correct answer. Any question?
No.
Question number 9 says the Avogadro constant is the same as the number of, or you have to do the calculation for all these. All right. The Avogadro's constant is the same as the number of electrons in 1 gram of hydrogen, is it? Or molecules in 16 gram of oxygen, or atoms in. Avogadro's constant is what? Can anybody tell me what is the constant? Avogadro's constant. Anybody? 6.023 times 10 power 23rd, right? 10 power 23rd. This is the Avogadro's constant. This is the Avogadro's number as well, we can say. Avogadro's number. So the question we have to find out, A, B, C, D, in which of them there is this number of particles, whatever it is, electron, molecule, atom, ion, whatever it is, but exact same number of this thing will be there. We see that electrons in 1 gram of hydrogen. 1 gram of hydrogen. And there is a trick here. All right. 1 gram of hydrogen means how many moles of hydrogen? How many moles? To find out the number of Avogadro's number, we have to find out the number of moles here. So 1 gram of hydrogen, gram over molar mass. Hydrogen molar mass is, what is the molar mass? 1.008, right? 1.008. But the thing is, 1.008 means there are hydrogen. It does not say is atom. It says what do you call it? Hydrogen gas. right? It's a hydrogen gas, and that is why in one hydrogen gas, that means we write in this way, hydrogen. This is the hydrogen we write. And one hydrogen atom, let's say this is the hydrogen atom, there is only one electron. And when there is a two hydrogen atom, there will be two electrons in it. I'll make it a bit better. The hydrogen, we write in this way that H2 is the hydrogen. And this is the hydrogen atom. It's one proton and one electron. There is no neutron in hydrogen atom. So if there is two hydrogen atoms, then there should be two electrons as well. This is another, this is electron, this is the center proton. So one hydrogen, H2, means two atom and two electrons, right? So for this case, what I will do is I will multiply it with 2, because there are two hydrogen atoms there, and then we find it is 0.5 moles. 0.5 moles, right? 5 moles. 1 mole of hydrogen atom has how many moles of electron? 1 mole of hydrogen atoms has how many moles of electrons? Can anybody tell me? H2, right? H2, that means two hydrogen atoms. Hydrogen atoms. So there are two electrons. So if it is 100 hydrogen, if it is 100 hydrogen, then there would be 100 times 2, 200 electrons, right or not? If 1000, then there should be 2000 of electron. If 1 mole, then there should be 2 moles of electrons. And then if it is 0.5 moles, there should be times 2, 1 mole of electrons there. 1 mole of electrons there. So since there is 1 mole of electron, it should be exactly same number of the Avogadro's number, because 1 mole. So there should be 6.0233 times 10 power 23rd number of electrons there. Okay. Is it okay? Upatish says okay, thank you. Others are okay with this? Silence means
yes.
Okay, good. So what about the molecules in 16 gram of oxygen? Now do it. In the class, I would ask the students to do it. And they cannot run away from here. But whatever. I will have Menti questions from second class onward. And that will be, the Menti questions are anonymous. So I don't see your name, who do it or who doesn't. But I expect everyone to do the Menti questions. From second class, I will have the Menti questions, okay? So now, electrons in 1 gram. So this is the correct answer. But why B is not correct? Molecules in 16 gram of oxygen. 16 gram of oxygen, right? When we say that 16 gram of oxygen, we see that oxygen is a diatomic gas, just like hydrogen. Actually, there should be more information given. Hydrogen gas, it should be called, and oxygen gas as well, it should be called. All right. So when is oxygen and hydrogen gas, we know oxygen is this way. Right. We know this one. Hydrogen in this way. chlorine this way, Cl2, H2, O2, N2. So this is the diatomic gas. That means they cannot stay alone as a gas. They must be combined with other atoms. Two atoms should be combined to become gas. So for oxygen, 16 gram of oxygen, and since it's a diatomic gas, so the molecular weight of oxygen will be 16 plus 16, 32. 32 gram per mole. So in this case, it becomes 0.5 moles. 0.5 moles, right? So since it's 0.5 moles, there are how many? I mean, how many Avogadro's number or how many particles of oxygen atom will be there? How many particles of oxygen atom will be there? Tell me. Can anybody tell me? Arlene? Out there? Kupati is typing. I'm expecting an answer from him. 3.011, yes, because you just divided the figure, right? So half of the Avogadro's, because it's 0.5, just half. So half of the Avogadro's number of particles will be there. So seems like it is okay for you guys to try. So try for C and D as well. Question number 10. It says that different quantities of nitrogen oxide are listed below. Which one contains the least number of molecules? Again, if this type of question, you have to do one by one to find out the correct answer. Least number of molecules. That means which one is the smallest number of the molecules, the lowest number. 6 times 10 power 2 liter at 273 Kelvin and 1 atmospheric pressure. It is given the volume and temperature and pressure. So we can use that PV equals nRT. nRT, right? PV equals nRT. If we use, and N is the number of moles. So if we find the number of moles, we can find the number of Avogadro's number, because one mole will have that Avogadro's number. Anything more or less will have more or less number of particles. So if we rearrange this equation, N will be PV by RT. RT. And from here we see that this is volume, V. V is given. P is 1 atmospheric pressure. So P is 1 atmospheric given. T is 273 Kelvin. It's already in Kelvin given. Otherwise, we have to convert from degree to Kelvin, but we don't need to now. And R is the universal gas constant. So for this case, since it is liter atmosphere Kelvin, so it will be 0.0821 moles per moles I think moles per Kelvin per I forgot what is that. Moles atmosphere liter per Kelvin. So in this way, all the Kelvin, atmosphere and mole that will be cancelled out. Only the number of moles will remain in this case. So we can find out from there what is the number of moles from this particle. Okay, so if you have calculator, please go ahead and do it. Another one is 6.6 times 10 power 23rd molecules already given. This is the number of molecules, right? And nitric oxide. So 6 mole of nitric oxide. Of course, it is not the case because if we multiply 6.023 times 23rd, so it is a huge number. It is, evidently it is not the case. It is not 6.02. 6.6 times 10 power 2 grams of nitric oxide. How do we find the number of moles? If we divide C, that means 6 times 10 power 2nd gram over the nitric oxide moles per gram, that is molecular weight of nitric oxide. What is the nitric oxide molecular weight? Can you tell me? Oxygen is 16, nitrogen is 14. So it will be 30, right? 30. So if we divide by 30, we will see it is a huge number still. 600 by 30 is 20 moles. So 20 moles is very big number. It's even more than 6 moles. So it is not the case. And for this case, even if it is a 1 mole, if it is 1 mole, if even, I don't know what is the value for this, but if it is even 1 mole, it will be more than this B, because B is 6 times, even less than 1 moles, right? This even less than 1 mole of Avogadro's number. So B is the correct answer for this. Okay, everyone? If question, please ask. Question number 11, it says that what is the mass of one acetic acid molecule? One acetic acid molecule, one molecule of acetic acid. What is the mass of one acetic? How do you know, or do we know that what will be the total? Where do we start from here? Seems completely lost. Where do we start? Okay, so we do not have anything, only we have the mass of one acetic acid, they ask us. But what we can say, do is molecular mass. We have the molecular mass with it from there. If we look and try to find the molecular mass of 1 mole of acetic acid, we will see that just sum up the carbon, 3 hydrogen, 2 carbon, 3 hydrogen, 2 oxygen, hydrogen is altogether 60 gram per mole. 60 gram per mole, right? Sorry, 60 gram per mole. And then that means in 1 mole, there will be 60 gram of acetic acid. All right, 1 mole, there will be 60 gram of acetic acid. And then in this, we can find another thing that since it is 1 mole, we know that this means 6.023 times 10 power 23rd number of molecules in there. I am always telling 6.023, but I am writing 2. Just punctuate it at 2 to express in 2 decimal places. Okay. And I remember in that way 6.023 times 10 power 23rd. So I remember the figure in that way. That's why it is my habit. It becomes. But if you write 6.023, you are also welcome to do that. Okay, so now we know that this many number of molecules are there. This many number of molecules are there. So when 60 gram means this many molecules, not moles, but molecules. So one molecule will have how many gram? We can find in that way, right? One molecule will have how many grams? So molecule per gram. If we divide this one by 60, then we'll find molecule per gram. But sorry, no, we need to find the gram per molecule. So 60 divided by this number of figure. So 60 divided by 6.023 times 10 power 23rd. So this is gram per molecule. In that way, we will find the mass of one molecule, and that is 9.97 times 10 power negative 23rd gram. Can you imagine how is the figure? That means after 10, you have to add another 23 zeros behind 1. 1 and then 23 0. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have just written half of it, so another half is there. So this is a very small number. Question number 12. Volume at standard laboratory condition of 0.22 gram carbon dioxide is equivalent to that of 0.1 gram of hydrogen gas. Is it 3.1 times 10 power 21 molecules of ammonia gas, 112 milliliter of sulfur dioxide at STP, all of them above? How do we find out? We have to find one by one. There is no other way to find out is the one. But first, we have to see the question. What is saying that the volume of standard SLC of 0.22 gram of carbon dioxide. So what is the volume of 0.22 gram of carbon dioxide? This gram means obviously it is a mass number. So if we see the volume, how do you find the volume of that? From here, right? We can find out the volume of carbon dioxide here from N equals V over V2, but then it is only gram. It is not the volume. It doesn't say it's the volume. So what we can do is we just, first of all, we can find out the number of moles of carbon dioxide. 0.22 gram of carbon dioxide means how many moles of carbon dioxide? Divided by 12.01 carbon dioxide. Oh, no, not 12. Sorry, it's not carbon, it's carbon dioxide. And carbon dioxide is 12 plus 16 times 2, 32 plus 12. So 44 gram per mole. If we divide 44, I round off again, so that it becomes 5 times 10 negative third. 10 negative third moles of carbon dioxide. Okay, so it becomes 5 times 10 negative mole negative 3 moles of carbon dioxide. Now we know that this is the number of moles. We know another thing is at a standard laboratory condition, if the number of moles are same, whatever gas it is, their volume will be same as well. We know that one from our previous studies, high school chemistry. We know that for same number of moles at standard condition or STP, they will occupy the same volume of whatever gas it is. So now, if we have this is the number moles, then we do not need to go and find what is the volume of this gas. We can just find what is the number of moles of hydrogen gas here. So 0.01 gram we have to divide by 2 gram of hydrogen gas, right? Hydrogen gas means, you know, that it is 2 because H2. So 1 plus 1, 2. So in this case, we see it is exactly the same number of moles. Molecules of ammonia, 3 times 0.1 times 10 power 20 first molecules, number of molecules of ammonia, and the number of moles we can find if we divide by the Avogadro's number, we'll find the number of moles for this case. And in that way, we also find this is the same number of moles. Same goes for here. This is the volume of sulfur dioxide at STP. So at STP, we know that it is the VL, the volume. Just now at the beginning of the class lecture, tutorial, we said that at STP, the VM is 22.4 liter, right? So if we divide by 112 by 22.4 liter, standard temperature and pressure, 22.4 liter, then we will see the number of mole is exactly same as this. So all of them actually are having the same volume as with carbon dioxide at the laboratory condition, 4.22 gram of carbon dioxide. Is that okay? Any question so far?
Sir, I have a question.
Yep.
To ask.
Sure.
I want to know that any type of gas that have same value of
number
moles,
of moles,
right?
yeah.
That means they have the same volume, is it?
Yeah, they will occupy the same volume at STP.
Okay.
Yes, that is correct. The number of moles are same. The gas, whatever gas, they will occupy the same volume. Okay, standard. This is the universal gas. Rule actually, the gas rule. It says that. Okay, the more detail we will read more when we go for degree. Okay. All right. So question number 13. It says that a sample of the insecticide dichlorphenyl trichloroethane, DDT, was found to contain 0.120 gram of carbon. What mass of chlorine was present in the sample? Now we need to, first of all, let me tell you something about the DDT. The DDT, probably you have not heard about it. It is a very good insecticide, very good insecticide. It is so good that it deletes or it kills everything. Not only insect, it kills bird, it kills animals, even it kills human. So it is a very big poison, bad poison. But one of the success of this DDT is in many countries or many places in the world, the malaria or the mosquito vector disease was eliminated because of this in 1950s or like that. So even 70, 80 years ago, the DDT was used, but a lot of birds and animals also extinct because of this. Okay, so this is the DDT, and it says that it was found to contain 0.120 gram of carbon. A sample of DDT. This is the formula of DDT, and it has 0.120 gram of carbon. So what mass of chlorine was present in the sample? What mass of chlorine we expected to be present for it to be in the sample? Now, this is two different things. It says about carbon, but asked about chlorine, right? Okay, so there are a few ways to do it, but at least two different ways to do it, but we do the simplest way, right? So 0.120 gram of carbon, right? 0.120 gram of carbon And we can see from the molecular formula that there are 14 carbon, right? There are 14 carbon, 14 in 1 mole. There are 14 carbon atoms, and there are 5 chlorine or chloride atoms in the molecule. From this molecular formula, we see that 14 carbon atoms are there and 5 chlorine atoms are there. We are not considering hydrogen because we are it only asks about chlorine. Now, if it is 14 carbon and 5 hydrogen, by equating it, that 14 carbon is equal to 5 chlorine, right? 5 chlorine, 14 carbon is equal to 5 chlorine. So 14 carbon means how many gram? 14 times 12, because atomic weight of carbon is 12. So 14 times 12 times 12 of carbon and is equal to 5 times 35. Chlorine is 35.5. 35.5. 1 atom of chlorine is 35.5. Sorry, not 1 atom. I mean, atomic mass of chlorine is 35.5. So now we see that if it is this gram of carbon is equal to this gram of chlorine, so 0.12 gram of carbon will be how many gram of chlorine there in this way. So we just multiply with this 0.120 gram of chlorine, right? Sorry, 0.12 gram of carbon, 0.12 gram of the atoms, gram of carbon, yeah, 0.12 gram of carbon times the chlorine and this thing. Let me write it here. So with this, we just 0.12 gram divided by the total gram of carbon. Total gram of carbon is 14 carbon is there times 12.01. All right. So in this way, we'll find that the chlorine percentage of, the percentage of chlorine will be 0.127. Sorry, the mass of chlorine will be 0.127. 127. Percentage of chlorine is 0.127 gram of chlorine here. All right. So A is the correct answer for this. Question number 14. Which of the following gas samples occupies the greatest volume at 298 Kelvin and 101 kilopascal? Let me drink some water. Okay. Which of the following gas samples occupies the greatest volume at 298 Kelvin and 101 kilopascal? How do you know it? Which of the following gas sample occupies the greatest volume? That means more volume. So which one has the more number of moles, isn't it? If we find the number of moles, 1 gram of ethane, 1 gram of oxygen, we have to just divide by the molecular mass of this, and in that way we will find this is 1 gram of neon has the more number of mass, so it will have the more it will occupy more. Question number 15, it says the different quantities of sulfur trioxide are listed below. Which one contains the greatest mass? Different quantities of sulfur trioxide are listed. Which one contains the greatest mass? Which one will have the more weight in it? So 8 times power 10 power 2 gram, that means 800 gram. 800 grams 0.8 kilo, and it is already straightforward. It is in mass, we know. 8 times 10 power 2 liter at SLC, standard laboratory condition. So if in that case, how do you find the number of mass of it? Again, we have to find N equals V over Vm, right? And Vm for SLC is 24.5 liter. So if we divide 800 liter by 24.5, so we'll know the number of moles for this case, and then from that mole we can convert it back to gram. And this one is number of molecules, it says. So it is obviously it is a little more than 1 moles of this sulfur trioxide gas, and this is 8 moles. So from here we see that is gram per mole is divided by sulfur trioxide. We'll find the number of moles from here, and from all the calculations it shows that B is the correct answer because it will have the highest number of moles from here. Okay, so any questions so far as we finish the self-testing question? No?
Sir,
Yep.
can you explain the abundance thing again? Like question 4, like question 3 and 4, the abundance. I still don't quite understand that.
All right, I'll go there. I'll go to question number 3 and 4 in a bit, but anybody has a everybody okay with this so far? 14, 15, anybody has a question?
Sir, I have question on number 14.
Yeah, sure.
Can I know why the noble gases are heavier? Like neon are heavier compared to fluorine, oxygen, and ethane.
It has to do with the atomic structure of neon, because in oxygen there are 8 proton, right? And fluorine it is 9, and in neon it is 10. So yeah, that is why it is much more heavier, because it has more number of protons and neutrons in it. All right, any other question?
No, thank you.
Okay. Okay, so question number 3 and 4, right? Let me delete first. Okay. All right. So before I go to the question 3 and 4, I go to the formula. Yeah. Probably it will be okay better. For us, the formula says that the relative abundance or average AR is what? Relative atomic mass. Oh my God, I forgot. So relative atomic mass, right? Relative atomic mass, the formula says that relative isotopic mass, respective isotopes, whatever isotope I have here, and their percentage of abundance, I have to use it. By total percent, this let me make it a bit bigger. This sign means the summation. That means it will sum up all the similar thing in a series. So plus the same thing again for the another isotope and its relative percentage of abundance, right? So this is the formula, the relative isotopic mass times percentage of abundance divided by the percentage of abundance, summation of the percentage of abundance. So for this case, we see that 54 mass number, isotopic mass is 54, and then its percentage of abundance is 8%. So it is 8% multiplied by this. Another one, there is another isotope. Atomic number, of course, same because that is the proton number. Another isotope is 56. Relative isotopic mass is 56, right? So it's 56, and the percentage of abundance is 92%. So multiply by 92%. And then it is divided by 8 plus 92. Divided by sum of these two. If there was another one, let's say 0.01, take 0.01% plus 0.01% like this. So the many it has, the more we will start adding here. So by this way, we go to the number 3 question. I think I can start typing is better. Typewriter. Okay, so for this case, it is relative isotopic mass for that particular element. It has 1, 2, 3, 4 different type of isotopes. Now it will be 203.97 times 1.48, and then plus 205.97 times 23.6, right? This is okay, plus 206.98 times 22.6. So in this way, we and plus of course 20798 times 52.3, and then I will be dividing this thing. Why this thing? I'll divide all those things. See, if you do not use the scale, what happens? A ruler. Okay, divided by all these percent of abundance sum together here. Percentage of abundance is 1.48 plus 23.6 plus 22.6 plus 52.3. So in this way, we can find out what will be the total mass. All right, total mass of it, of the particle. So this is, I'm just using the formula what was given in the lecture and also at the beginning of this tutorial. And for question number 4, this is the question number 4. Question number 4 is just the opposite half is given. All right. It is saying that the relative atomic mass is already given. I need to find out the percentage of abundance. Like now it is asking me about this percentage of abundance, but relative isotopic mass is given. All right. So for this case, what I will do is, since the relative isotopic mass 186 is given, so I'm replacing AR from here. This is equal to AR, right? From the formula we have seen AR is equal to this formula. So 186.2 is equal to, what will happen? We do not know what is the percentage of abundance, right? We do not know any of the percentage of abundance. So we will just consider X. Another one is 1 minus X, because total, this total is 100%. It should be 100%. 100%. But if you take the fraction of it, 100% means 1 as well. 100% means 1 as well, because the total fraction we are taking. So 1, I'm sorry, 186, right? 186.2, this is the total atomic average atomic mass. So this one is equal to 185. Let's say 185 times the percentage of abundance, as the formula says, and the percentage of abundance we do not know. Just consider X or any other. You want to consider A, B, C, D, whatever you say, you just say, but you need to mention what the X percentage of abundance plus 185, the X is taken. Oh, this one. So how much percent should be, because there are only 2. So if one is X, another one should be 1 minus X. If it is 3, then we cannot solve in simple way. We have to find out a higher math. So for simplicity, it will be 2. So there is, if 1 is X, 1 should be 1 minus X for 187. And then if we solve the equation and find out what is X, we will see it is 60 in this way. Sorry, it's not 60, it's 0.06 because we are taking the fraction. So 0.6. So 0.6 means, since 1 means 100, 0.6 means 60%. All right. So is that okay? Who asked the question? I didn't see your name. Is that okay? Okay, good. Now, what is the time now? Almost. The good thing about this past year question is these questions are all given in the, what do you call it? Where is it? It's all given in the solution manual, because the solution, you can find the solution under feedback, and I'll open it after the class. So for this case, this is a boron, sorry, bromine. It's a bromine. 35 is the proton number, of course, proton number. And for neutron, what will be the neutron then? It's 79. So 79 minus 35, right? 79 better that I use here typewriter. So it will be 79. Yeah.
44, right?
Oh, okay. Yeah, maybe I just show you how to do 35, how to do it. So from here we know that is 44. Yes, thank you. Right. And electron is 35 because there is no charge here. So electron is 35. What about this case? Number of protons. For bromine, since it is bromine, number of proton is always 35. And for this case, bromine, there is one negative charge. So how much it will be?
36.
Yes, good. 36 electron. That means one electron excess more than the proton. And that is why it is negative charge. Why? Because electron itself is negatively charged. So since electron is negatively charged and there is only one charge is showing here, I should have to have one excess of electron. That is only then it will show me the 36. I mean negative charge. Okay, so question number B, abundance, isotopes, and the same thing. Calculate the relative atomic mass of bromine. So how do you do it? Again, the same thing. Sorry. Just hold on, yeah. Okay, so calculate the relative atomic mass of bromine. Give your answer to 4 significant figures. All right, and then 4 significant figures means this is a 4 significant figures. Sometimes pencil is important, sometimes typewriter. So this is all are 4 significant figures. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. So these all are 4 significant figures, right? So now it is asking us that whatever, if your answer is, let's say 359, I'm just giving a 359.85. And it is asking you to give 4 significant figures. You cannot give in this way. It is already 5 significant figures. You should have to give 359.8. Altogether, it should be 4 significant figures. Also, it can be said that 2 decimal places. All are 2 decimal places. That means there are 2 significant figures after the decimal point. So it is 2 decimal places. If the question say give your answer to up to 2 decimal places, then this figure is acceptable. Okay, this figure is acceptable, not this one, because this is 2 significant figures, decimal places. This is 1 decimal places, so it will not be acceptable in that case. But when you say 4 significant figures, all together it should be 4 significant. Or if it is, let's say that 30 point, just example 30.20, and it asks you 4 significant figures, you have to express this 0 as well. You cannot omit or say, okay, it's 0, I don't want to put. No, you have to put this one because it's 4 significant. Altogether, it's 4 significant figures. Okay, so this is it. Relative atomic mass. How do you do it? Oh my God, I need to delete it all. I need to delete all these things. Okay, so calculate the relative atomic mass of bromine. Give your answer to 4 significant figures. So exactly same thing, which what we have done. That's why I spend much time on the self-testing question so that it will be easier for you to do. Exactly the same thing. We multiply these two and these two and divide by the percentage of abundance. Percentage of abundance is almost always 100%. Of course, it will be 100%, right? Almost always. If it is 99.99%, don't worry. You just consider 100%, 99%. So in that way, we can find out the percentage of abundance here. So inform below it about the compound X. Define empirical formula and molecular formula. What is empirical formula? Empirical formula is the simplest, smallest, lowest, simplest ratio, like carbon, hydrogen, and oxygen is there. And I have carbon 2, I have hydrogen 6, I have oxygen, let's say 10 or 8 or whatever. So the simplest is I can divide all of them by 2 and express it CH3O5. This is the simplest. I cannot make it even smaller than this. It should be whole number. So this is the empirical formula, but the molecular formula is this. Empirical formula does not tell the identity of the molecule, but molecular formula does. It tells the identity of the molecule. Okay, so this is the simple and similar thing actually what we have done so far, almost similar thing. All right, so this is it for today. If you have any other question, or if you want to have further discussion, another separate session, please let me know so that I can arrange it for you. All right. Do you have any questions so far? Cannot round up. What do you mean round up?
Sir, just now the figure was, there was 5 significant figure, right, just now. So the last number was 0.85. So what I meant was, can it be 0.9?
Yeah, I understand. No, if it says that 5 significant, where is it? I deleted it. Yeah? If I think I will talk more about it during the lab, how to take the data. So if it says the 5 significant figures, don't round up, just keep that. And you do not have any other figure, so you do not round up, you just keep it as it is. Because you have to express in 5 figures. Right? You round up and it becomes 4 significant figures, then you lose marks there because you don't follow the instruction in the question. Okay. But if it is let's say at 35.2, 3, and 7. Right, and it is asking you to express in 5 significant figures. So you express as it is, whole thing. You 4 significant figure, then you round it up, the 3, 4, 35.2, and you express in 4 significant figures. All right, but if it is 3 significant figure, then you just delete or omit this thing. Don't need 35.2 only. It will be so in this way. Right. Okay. All right. So is there any other question do you have?
Sir, the remaining questions we will discuss it in the next meeting, is it?
No, remaining questions, because it is very similar to what we have done in the self-testing question, and the answers are given in details in the solution manual that I will make it available just now after the class. So yeah, and these are all the same questions, actually similar questions. So that is why I'm not going to discuss further about it. But if anybody has any specific question, any problem, then please let me know so that I can arrange a time for you and then discuss more about it. Okay.
Okay.
All right. So all the best. I'll see you next class Monday. Have a nice holiday. I mean, weekend.